the suite of features. So it's well known, but it's not really well adopted in the enterprise. So we'll kind of take a look at how it works and how attackers kind of have to change based on these mitigations. So about me, my name's Connor. I'm one of those dumb developers you heard about earlier at CrowdStrike. I'm on Twitter and I have a blog, and I'm pretty much interested in anything C assembly development related. So today we'll kind of talk about what Windows exploitation looks like in its current state. We'll take a look at the internals of the mitigations, which we're going to speak about. Then we'll see how that kind of affects exploitation. So when it comes to exploitation today, attackers have a few different options when it comes to taking advantage of what we would call memory corruption vulnerabilities. And the way that this usually occurs is an attacker will try to execute some sort of unsigned code or shell code, as you're all familiar with. The reason for this being is most C2 frameworks, for instance, they have a shellcode blob they run because they call into Windows APIs, which are a suite of exported functions on Windows that allow you to open network connections, etc. So when you do that in pure shellcode, it easily allows you to call those functions, set up arguments, etc. And it's the path of least resistance. So most exploit chains today, though, they take two separate exploits. And the reason for this being is popular initial access targets like web browsers, they're sandboxed. So an attacker exploits a web browser, for instance, the code execution they have is only in context of a very low privileged sandbox, essentially. You can't open up network connections, do any of the things we want to do, drop files, etc. So what they'll try to do is they'll try to privilege escalate from there. And the main method of that is through the Windows kernel, because obviously it's accessible to anyone that uses the OS. So the way that this works is it's a three-step approach. So attackers, on modern operating systems, there's really no read, write, execute memory by default. So they'll find a writable portion of memory where they can write their shellcode to. They'll use some sort of first-staged payload to mark that shellcode as executable, because remember, that memory is only writable, it's not executable. And then they'll do something called control flow hijacking, where they force the target to execute that memory, which obviously it's now executable, and so it's going to run your shellcode. And in the Windows kernel, here's kind of how this looks, a high-level diagram. So basically, we got the memory address FFFF780 sign extended, and it contains some shellcode in the red. And we can see the acronym PTE below, which stands for page table entry. That describes this memory region. So what this is saying, the K stands for kernel. It's a kernel mode memory address. W stands for writable, and V stands for valid. So we've taken care of the first step, which is writing some shellcode somewhere that's writable, but it's not executable. Then an attacker will use some sort of second stage payload, which we talked about, and they will find the page table entry that corresponds to the memory. So the page table entry describes that page. It says, hey, this is readable, writable, etc. They locate that metadata and they corrupt it. And so now when the memory manager, when the CPU goes to execute this instruction, it looks at the metadata and it says, oh, this is executable. That means there's code that needs to be executed there. So we've gone from a writable page to executable page. And then on the right-hand side, we can see that we overrode a function pointer. So as the name infers, function pointer points to a function. So we override it with the memory address of our shellcode. So what will happen now when this function pointer goes to be executed? It's going to execute this memory address, which is a malicious address that contains shellcode, which is now executable. So that's kind of that three-step approach we talked about. This is actually mitigated. So that was a kernel mode example, but in user mode, where typical users operate, that's actually mitigated with a mitigation called arbitrary code guard. And what that does is it basically says, it's Windows implementation of write, XOR execute, which means memory can either be writable or executable, but never both. So in our example, what we did was we corrupted the page table entry to make memory that was writable executable. Well, that violates the tenet of arbitrary code guard, that memory can't be both of those things at any one time. But that's a user mode mitigation, arbitrary code guard. And the reason why that's a user mode mitigation is because the mitigation itself is implemented in the kernel. So we have a user mode, kernel mode security boundary. So if we implement the mitigation in kernel mode, well, attackers in user mode, they can't corrupt the integrity of that mitigation because it's protected by the kernel, right? But in our example that we showed, it was a kernel mode exploit, right? So if you try to implement a mitigation in the kernel, but your mitigation works off of the fact you're trying to block attackers that already have access to the kernel, that's basically the kernel trying to defend against itself, right? If I'm an attacker and I have access to the kernel, you put a mitigation there, well, I'll just disable the mitigation and then go on my merry way. So we need to address this problem of how do we address this if the kernel is the highest security boundary essentially on the OS. And that's exactly what we'll talk about here. We'll talk about Hyper-V. We'll talk about VBS, which is Virtualization-Based Security, and then HVCIs a little later. We'll get to that. VBS, or Virtualization-Based Security, it's, as I mentioned, a suite of features enforced and provided by Hyper-V. This suite of features, as I mentioned, if you're familiar with it, you're probably familiar with Credential Guard, for instance, which is one of the security mitigations offered under the umbrella of VBS. And what VBS does is it works off of Hyper-V, which is Microsoft's hypervisor. So since Hyper-V is responsible for enforcing VBS, it's worthwhile investigating the design. And Hyper-V works off of the notion of partitions. So the root partition is what's called the host OS. So what happens is with Hyper-V, when your machine boots, the root partition fills the entire physical address space. That's your host operating system, right? There shouldn't be any VMs running at that point. So as VMs are created, those create what are known as child partitions. And those child partitions are basically just a set of resources that host a virtual machine. And as I mentioned, the root partition takes up the whole address space of the computer, and then anytime we create a virtual machine, we allocate from that root partition. Here is an example, a diagram of this taken from the MSRC blog. As we can see, we have the root partition and the child partition. They both run on top of Hyper-V. The child partition doesn't run inside of the root partition. As I mentioned, the root partition gets allocated from as child partitions are there. So basically, we can just think of this as root partition, that's your host OS, right? That's what we use on an everyday basis. Child partition are instances of virtual machines, essentially, and they run on top of the hypervisor, which is Hyper-V. A child partition, as I mentioned, is allocated from the root partition, right? So that means it has its own address space. And it has its own address space because we want to isolate it from other child partitions and the root partition, right? Like if you've ever ran malware before, you want to run it in a VM, generally speaking, barring any vulnerabilities in the hypervisor, because it's isolated, right? But how does that isolation actually work? There's a technology on modern CPUs called SLAT, Second Layer Address Translation. And Intel's implementation of SLAT is known as extended page tables. And what SLAT does is it allows the CPU to intercept VM memory access, essentially. And the reason for this is because VMs just act on memory, as we'll see in the diagram in the next slide, as if they're the only OS running, right? You don't know about other VMs at a high conceptual level. So something needs to compensate for that, because what if we have multiple VMs running, for instance? So if we look at this example, on the right-hand side, outlined in the red, we'll call that our child partition, which is a VM running, right? It runs inside of in the computer, essentially. And then we have the root partition there, which is total address space, and the child partition is allocated from there. Here's the issue though, right? So if we look on the right-hand side, you can see like any of those memory addresses. Let's choose 0x1000, for instance, on the right-hand side. Well, on the host OS, that's actually located at 0x4000, right? So the VM maps, 0x1000 as, oh, I'm just going to access 0x1000. Well, 0x1000 on the host OS is unmapped, right, up there, and that's where the VM's running, so that's where the memory technically lives. So what SLAT does, basically, it says, hey, I see this VM going to access 0x1000. That's actually located at 0x4000. So let me perform translation so that the VM knows, hey, even though it thinks it's accessing 0x1000, that memory is actually somewhere else on the host. And the way that this is done is by managing an additional set of page tables. So page tables basically contain all the necessary information to perform memory translation. So what happens now is every VM is associated with an extended page table set of page tables. And the CPU basically knows that, and it knows to associate each set of page tables with a given VM. So let's say VM1 goes to access 0x1000. The CPU knows, hey, I need to access the page tables from VM1 so that I know I can translate 0x1000 into the actual memory on the host OS. And the way this is done is VMs emit something called GPAs, or guest physical addresses. So the VMs just act on memory as if they're the only OS running, and then the CPU behind the scenes intercepts that and translates that into actual memory on the computer. So as we can see in this example, the VM in the bottom left, it accesses a memory address, which gets translated in context of that VM. Then that gets emitted, and the CPU intercepts that and says, hey, I see you're going to access 0x1000. Let me look at the virtual machine control structure, or VMCS, which contains your VM's page tables, and see where that memory actually lives on the host OS. So this is actually the technology that allows VMs to remain isolated, because the CPU handles all of the translation. VMs can only access the partition they've been allocated. And what VBS does, it basically abuses these principles for security purposes. So now we can isolate sensitive parts of memory, basically how VMs are isolated. But instead of using virtual machines, VBS implements something known as virtual trust levels, or VTLs. So as we can see here, VTL 0 is what we refer to as normal mode. So you boot up your machine, it's got VBS running. You don't really know it, it's not transparent to the end user, and they're operating in normal world. So you have your typical user and kernel mode over there. But now we have a VTL1, which is known as secure mode, which contains the secure kernel that can basically protect all of the secrets of the OS itself. So we can think of this as when you run your machine with Windows, with VBS enabled, you're kind of running in a VM of sorts. So we don't have virtual hard disks or networking or anything like that. VTLs are just an isolated segment of memory, just like a VM is. So as I mentioned, that's what a VTL is. So we can isolate one VTL from another, just like we can isolate VMs from one another. And this allows hypervisor protected code integrity, or HVCI, which is the mitigation we're going to talk about, to work actually. So HVCI is another mitigation, just like Credential Guard, that falls under VBS. And this is the answer to the question earlier of how do we stop shellcode in the kernel, because we know we have arbitrary code guard in user mode, but that mitigation is implemented in the kernel. So if an attacker in user mode wants to try to disable arbitrary code guard, well, you already need access to the kernel. But if the kernel's a high security boundary, how do we stop kernel mode code execution if we assume an attacker already has access there? So what happens is VTL 0 and VTL 1 are placed in the root partition. So there's no child partitions anymore. We place them in the root partition, so they technically have access to the same physical address space. And since they have access to the same physical address space, we don't really need to use the extended page tables for translation anymore. So HVCI abuses them for a different purpose, and that's to create an additional set of page tables with an immutable set of permissions. So what that means is VTL1, which is secure world, when the system boots, VTL1 can ask the hypervisor, hey, I want to configure the extended page tables with these permissions. And the hypervisor manages those. So now what happens is if a kernel mode exploit in VTL 0 tries to use the page table entry, which we talked about earlier, that metadata, which describes a given memory page, well, we have a source of truth now that's managed by the hypervisor, and the hypervisor is a higher security boundary than the kernel, so therefore you can't create dynamic executable memory. Here's kind of what that looks like. So in this example, we have a memory address, and we have a PTE, which we saw earlier, so this describes this memory page as writable and readable. Then we have an associated extended page table entry, which again is managed by the hypervisor. So if we do the same thing as last time, we corrupt the PTE, which are stored in the kernel, and we make it executable, well, the hypervisor says, no, wait, actually, this is still readable and writable because those extended page tables are actually the source of truth and they're managed by the hypervisor, and the kernel can't directly access the hypervisor. And the way this works is we use the exact same concepts as we did with the virtual machines. So with a VM, when it goes to access some memory, what can the CPU do? It can intercept that or gate that access. That's exactly what we do here. Anytime VTL0, which is the normal world or untrusted world, anytime we access memory, the hypervisor can gate that memory access, just like a VM. We can intercept that, and we can say, hey, we see you're trying to execute this memory, but actually, our version of memory, which is immutable from the kernel, it says it's not executable, and therefore, we're not going to let you execute this memory anyway. So we can dilly-dally in the kernel all we want, corrupting all the page table entries to say this memory is executable, but the hypervisor has a source of truth, and it's immutable. So to summarize this, VTL1 sets up the proper permissions of memory. So what VTL1 is responsible for here is setting up, just like arbitrary code guard, write, XOR, execute. No memory is ever both writable and executable, which is a prerequisite for shellcode. All of those extended page table entries that contain the ground truth are protected by the hypervisor. So even an attacker in kernel mode can't arbitrarily access the hypervisor to corrupt that metadata, essentially. So now that we know this information, let's see how this affects exploitation. So we've talked about using HVCI for enforcing executable permissions, correct? So thus far we've said, hey, with HVCI enabled, we can't just make our own executable memory to start executing shellcode. But another interesting thing about HVCI is we can use those same principles to protect other sensitive parts of memory, such as the kernel control flow guard bitmap. So what kernel control flow guard is it's the kernel mode implementation of CFG, or control flow guard, which is a mitigation that's been in Windows since Windows 8.1. It was an optional update then. And what CFG is, it's mitigation that checks all indirect function calls to ensure function pointer hasn't been overwritten. And the way this is done is a bitmap is created of all of the known valid functions that are used in indirect function calls in a given application. So you develop your application, you may call into 5 different functions. At compile time, a bitmap is created with that information, and any time an indirect function call happens, we check that bitmap to say, hey, is this a valid call target? Is this a legitimate function we know about? If it's not, we crash a process. And that may sound a bit confusing, but if we go back to our original example, what allowed our shellcode to execute? We had to overwrite a function pointer, right? And when that function pointer was executed in the future, it redirected execution into our malicious shellcode. Well, now that's called an indirect function call when that happens, and that's now checked by kernel control flow guard, and that will crash the process essentially at that point because we've done a malicious action. So KCFG runs into the same issue as trying to implement arbitrary code guard in the kernel, right? Normal control flow guard is protected by the kernel, the bitmap. But when you try to implement a mitigation in the kernel, as we talked about earlier, and you assume an attacker has access to the kernel, well, that's, again, the kernel defending against itself. We can't do that, right? Because an attacker could just disable the mitigation before they deploy their attack in the kernel, for instance. So we've got to do something about that. We do the exact same thing as HVCI, except we do it on read-only permissions at this point. So what HVCI does is it protects the KCFG bitmap, and it says, hey, this bitmap is read-only, because if an attacker can make it writable, they can mark all of memory as valid call targets and call into whatever memory they want, right? The point of KCFG is to prevent function pointers from being overwritten. So we do the same thing here. In this example, it's a debugger. In the bottom right where it says PTE, that's the page table entry that corresponds to the kernel control flow guard bitmap. And I've marked it explicitly as K, kernel, which it already is, and W as writable, right? But then I use the EP command to try to override it with some junk data, and look at the error I get, memory access error. That is HVCI saying, hey, the extended page table that maps to the bitmap is read-only. Even though in the kernel you've said it's writable, the hypervisor views it as read-only, so we block the write operation essentially. And that's how we protect kernel control flow guard in the kernel. So with HVCI enabled, in totality, here's where we stand. We can write our shellcode all day long to kernel mode memory that's already writable, but we can't make it executable. And even if we could make it executable, anytime we try to override a function pointer to go to execute that shellcode, kernel control flow guard will prevent it. So this puts us in an interesting predicament. So what do we do about this? So as I mentioned earlier, what is shellcode used for? Shellcode, as I mentioned, like a C2 framework, well, it's a blob of shellcode that calls into various Windows APIs, right? So you may have a function, a Windows API called open process. Maybe you're familiar with that. That's to obtain a handle to an object, basically. That's what C2 frameworks will do. They'll call into these APIs in ways they weren't intended to open up network connections, read files, write files, read memory from other processes like LSASS, for instance. So we know that's what we want to do with shellcode, but we can't actually execute shellcode. So what if we could do something that was HVCI compliant, but accomplishes the same thing of calling into Windows APIs? Well, the main issue that's facing us is how do we gain execution? Kernel control flow guard is going to prevent us from overriding a function pointer, for instance. But that's not the only type of control flow transfer that's available. What about returns for instances, right? In assembly, when a call instruction happens, what happens at that point? A return address is pushed onto the stack, and that's just if you, in C, for instance, if you have a function body, what does it normally end with? A return. It returns a value to the function which called it. In assembly, what happens is a return address is pushed onto the stack, and when the function is done executing, it uses that address to know where we need to return execution back to. Well, as I mentioned, it's used to return execution somewhere, so it's also used in a control flow transfer. One of the known limitations of CFG in general is return or backwards edge control flow transfers. Kernel control flow guard only investigates forward edge or calls or jumps. It doesn't investigate returns. So what if we could override a return address on the stack, right? If you're familiar with your typical 32-bit no ASLR depth buffer overflow that most people do as their first exploit, that's what you do. You don't, people use a term like, oh, I overwrote EIP, for instance. You didn't overwrite EIP. You smashed the stack and you found a return address on the stack. You overwrote that return address, and eventually that return address was loaded into the instruction pointer. So we kind of need to go back to the basics, if that makes sense, but we can't assume we have a stack overflow. And we need to leak the stack of a kernel mode thread. Luckily enough, Windows blessed us with this gift, a function exported by NTDLL called NTQuery System Information that will gladly give us kernel mode addresses from user mode from a medium integrity process. So medium integrity process, that's basically any application you open up on Windows. So what we can do here is we can create a thread in user mode, and we could put that thread in a suspended state. Then we could call NTQuery System Information, which is accessible from user mode, and that would give us the kthread object associated with that thread. And a kthread object, as it infers by the first letter in the name, K, kernel. It's the kernel mode representation of a thread. Thread is an object that's managed in the kernel. So basically, we can leak the thread, we can leak a kthread object from the kernel of any thread we create in user mode, basically, by design. And each user mode thread has a user mode stack and a kernel mode one. Now you may be thinking, Connor, this doesn't make sense. You created the thread in user mode, but you're telling me you've leaked a kernel mode thread. Well, that's because every thread on Windows has both a user mode stack and a kernel mode stack, regardless if you create it in user mode or kernel mode. So what we can do is we can basically use native functionality in Windows to leak a kthread object associated with a thread we control. And if we look in kthread, there are two members of that object called stack limit and stack base. As it infers, that's the stack. And what's on the stack? Return addresses. So since we know we can leak the kthread object associated with the thread we control, which return address do we want to target? So we see a bunch of these return addresses on the stack. This is what a call stack looks like for a newly created suspended thread. And we're going to choose KIAPC interrupt as our target address we're going to overwrite. This is all going to make sense in a little bit. And the reason why we're going to choose this one is because a suspended thread on Windows is actually just a thread that has what's called an APC, or an asynchronous procedure call, queued to it. And that APC tells the thread, don't do anything. And what an APC is, it's basically a code root. It's basically code, just like a thread. A thread executes code. But instead of executing code in a thread, that code is executed in context of a given thread. So what happens is, with an APC, a sort of software interrupt gets issued that calls an APC, which tells the thread, hey, don't do anything, which sounds like a suspended thread that's not doing anything. And the way you resume this thread, or the way the thread can start executing again, is it's basically waiting on an object, and that is the suspend count. So until the suspend count of a K thread is 0, your thread is going to be suspended. So when we call suspend thread, or when we create a suspended thread, suspend count is set to 1. And we decrement that by calling resume thread. So if you think about it, without knowing any of this lower level knowledge, quote unquote, if you create a suspended thread and you call resume thread, that should theoretically resume your thread, right? What that's actually doing is it's incrementing and decrementing suspend count. And the reason why this is even important at all is because we know that when we create a suspended thread, we know an APC should always be queued, and therefore that return address should always be on the stack. Now, using a kernel mode vulnerability, we have the stack, right? We can locate return addresses, we can corrupt those. Then when the return address is executed, it will call into our fake return address, basically. So if we look at this, in this example, in the top screenshot of our exploit, we've leaked the stack, which we've done no exploitation up at this point. This is perfectly legitimate Windows exported functionality that I encourage you to try out on your own. So we've leaked the stack, but then we use our kernel mode vulnerability, which again, now we're getting to the vulnerability part, where we corrupt that return address with 41414141. And look what happens. We get an access violation, even with kernel control flow guard implemented. Because what happens? When that return address gets executed, it's now trying to execute 41414141. So basically, we've proof of concept that we can control the stack. We can control execution at this point. So with the control of this, we can basically do a code reuse attack. If you're familiar with the term return-oriented programming, or ROP, that's probably the most mainstream of them. We can't execute shellcode directly, but what does shellcode do? It calls into Windows APIs. We can do this in pure return addresses. That's what return-oriented programming infers. And that's basically mimicking our shellcode. So we can't just set up a shellcode blob anymore, but we can kind of do the same thing shellcode intends to do. So what is ROP? Just a high-level ROP is basically flooding the stack with a bunch of fake return addresses, essentially. And each fake return address does some sort of interesting code sequence, and it ends in a return. And the reason for this being is because what a ret actually does, a return instruction, it takes whatever's located on the stack pointer, and it will load that into the instruction pointer for execution. So by nature, every time what's called a ROP gadget, which is that series of instructions, is executed, when the return happens, what does it do? It looks at the stack, picks up what's ever there, and executes it. Well, if we flooded the stack with fake return address, every time we execute a ROP gadget, it's going to go pick up the next one, and the next one, and the next one. And here's an example of this. So we pretend that we control this stack, which we do in our exploit, and what do? We flood it with fake return addresses. And what we do is we set up a function call by setting all of the functions in the proper registers. So each architecture has a calling convention, right? On Windows 64-bit systems, by default, it's the fast call calling convention. And what that means at the assembly level, whenever you call into a function, if you actually looked at the disassembly, each one of your arguments that you passed is loaded into various registers, namely RCX first for the first argument, RDX, R8, R9. So that's what we do here. We load up our arguments, and then we return into the function. So basically, this is a way to call the function virtual protect in pure return addresses. And the reason why we do that, again, is because that's a code reuse technique. We are reusing code that's already executable. We can't just supply our own. We have to find code because, again, applications are made up of code. So we know we can basically do the shell code via ROP. So what is this useful for? So let's do an example, right? We have a kernel exploit. Let's try to do something interesting, like terminate the MS-MP-eng process, which is the Windows Defender anti-malware service process. So if you've ever heard of the term PPL before, Protected Process Light, this is basically a type of process that is special in a way. So in this case, this MS-MP-eng, it's what? It's an anti-malware process. So AV vendors are afforded the ability to make their process a PPL, and in this case, it is an anti-malware PPL. And what that means is it prevents other processes, even administrators, from tampering with it, right? So it's a special kind of process that only the kernel could do something with. As we see in this example, even with a command prompt running as administrator, when we try to kill the process, what does it say? Access denied, because it's afforded special protection. So we know we have a kernel exploit. Even with HVCI enabled, we know we can call into Windows API, so let's see if we can't do anything interesting. So as I mentioned earlier, a handle, I'll give just a brief overview, it's not in the slides. A handle is an intermediary way to interact with an object, right? So a process is actually a object managed by the kernel. So we can't just access that directly, right? But we can open what's called a handle to it, which basically is a proxy, almost like an API of sorts, that allows us to request a given action be done. So we could open up a handle to LSASS, which is what attackers do, and they might call mini dump write dump, which is a Windows API function that dumps the process memory. You need a handle to do that. So in order to terminate a process, we need a handle. But we know it's a PPL, so even as an admin, we can't terminate it, right? So we need some sort of kernel exploit to do this, which we already have. So we need more than just admin access, essentially. We need to actually get our handle to this process from the kernel, right? Even an administrator cannot just arbitrarily open a handle. We need to do it from the kernel. Well, we have an exploit primitive to start calling functions in the kernel, so good for us. We can call into the function ZW open process, which is a kernel-only API call that, as it infers, opens a process handle. So using ROP, basically here's an example. Once we control the stack using all the aforementioned steps we talked about, we can flood the stack with fake return addresses, and in this case, we populate arguments in registers that eventually call into ZW open process, and this is what it would look like. We leak the stack, we corrupt all the return addresses, and we're able to call into ZW open process. So that alone would give us a handle to the Defender anti-malware process, even though it's a PPL. But there's a bit of an issue, and that's because we're in the kernel now. So what happens anytime there's any kind of fault or issue in the kernel? You get a BSOD, a blue screen of death, right? So we've just totally smashed and just mashed the stack with garbage, essentially, that we control. And there are legitimate return addresses that need to be returned into critical functions, right? So if we just let bygones be bygones there, we're going to just cause a BSOD, a blue screen of death, essentially. So we need some way to avoid that. So what we actually want to do is we want to find a way to actually terminate the thread that our exploit's running in, because as we talked about earlier, we've created a dummy thread to do all this exploitation work in, right? We don't care about it necessarily, but we need it to gracefully terminate. We can't just let the kernel, handle a fault because it may be devastating. So basically, we just append our first ROP chain with a second ROP chain that invokes terminate thread. So we have a handle to our dummy thread. We just pass that handle into terminate thread, and after we open the handle to defender process, terminate thread lets the kernel handle all of the termination of our thread. So we don't need to worry about cleanup because the kernel is going to handle it for us. So basically, after our exploit work is done, we call ZW terminate thread, and that's going to terminate the dummy thread gracefully, and we're not going to get a blue screen of death. So here is the last set of issues that we're facing here. And these are more just about the creativity of exploitation, not really HVCI. So we want to pass the defender process handle to the function terminate process, right? Because we want to terminate the process. Although we have a handle to the process, there is an issue that we're facing. It's actually two issues. The first being handles are stored in a per process handle table. So what that means is every time a handle is open, that's managed by a table in your process. So our exploit process, let's say it's called exploit.exe, right? Well, that's got a handle table of all of the handles that are opened stemming from exploit.exe. Yeah, so let's talk about that a little bit. So they're in a handle table, so we're going to have to resolve that in a second, being able to locate that handle. But the main issue is that anytime a handle is open to most anti-malware processes, something happens. And sorry, I'm losing myself here. Let's talk about this, as I just mentioned. So anytime in a anti-malware process, you can register, since you're a special type of process, these kernel mode callbacks. You may have heard of these before. And basically what a kernel mode callback is, it's a function you register in the kernel that anytime a given action happens, any function that was registered is notified. So for instance, you can register a callback function for process creation. So let's say Defender registers a kernel callback for process creation. Anytime a process is created on the whole OS, that Defender process callback is called. So that's how your anti-malware utilities know a process was created, right? Well, there is also a callback you can register for object creation. So anytime you open up a handle, any security product that registered a callback will get notified that you've created a handle. And what Defender does is anytime you try to open up a handle to Defender, that callback will strip the access rights from it. So you can never open up a handle to Defender with the needed permissions to terminate it from user mode. And the second issue is that even if we were able to open up a kernel handle to this process, anytime you open up so let me explain this. We opened a user mode handle. So even though we called a kernel mode function, as I said, it's in our per process handle table. So exploit.exe is responsible for opening up that handle, right, to the Defender process. Well, that means that handle will be stored in exploit.exe's handle table. But we want to open up a kernel handle to it because anytime you do a user mode handle to the Defender process, you're going to get your access rights stripped. But the issue is, if you open up a true kernel handle, which we'll talk about in the next slide, a true kernel handle, that will get stored in the system processes handle table. So now we run into an issue where even if we get the necessary handle, it's stored in another process's handle table. So when we call terminate process, it will try to look up in our handle table all of the handles, and it won't find it because it's located in another process. So the first issue is we need a true handle. We need a true kernel handle. So the way we do this is when we call ZW open process, we got to supply a structure here called object attributes. And there are a few options you can set here in attributes. One of them being obj kernel handle. As the name infers, this is going to make this handle what? A kernel handle. So basically now when we call into this function, we supply this, and the handle will be opened up as a kernel handle, which means Defender won't strip the access rights. And this is how this is done. So basically we can just set 0x200, which is the notation of obj kernel handle, the actual value. So great, now we have a kernel handle. So we know we can terminate the process now. But the issue is, when we call terminate process to actually kill it, where is that handle located? In the system processes handle table, which we cannot just arbitrarily access. So we need to think a bit outside the box here. So what if we could actually force our process to think it needs to locate all of its handles in the system process table? There's actually a way to do this. You need a kernel mode vulnerability, but basically we know we can leak k-thread objects, right, of all threads. There is a member known as previous mode. And what previous mode is it's a way to denote where execution came from when a system routine reaches the kernel, right? So if you're familiar with system calls on Linux, right? Like you load a system call number and you invoke syscall. That's actually true on Windows, but it's abstracted from you. So what happens is, for instance, when you call virtual-alloc to allocate some memory, that's actually just a wrapper which calls another wrapper, which eventually goes down to the NTDLL layer, which invokes NT-allocate virtual memory, which does the same thing, loads a syscall number and does syscall. And what syscall does is it transfers execution into the kernel to allocate some resources for us like memory. So when that system call happens, previous mode is always 1 when it comes from user mode. So the kernel knows, hey, this is untrusted input from user mode. Let me do some security checks. But when previous mode is 0, this means that the system call originated from the kernel itself. So what if we used our kernel vulnerability to make the kernel think the handle it needs to resolve is from the system process handle table? Well, if we look at the actual system call that's responsible for terminating a process, which in this example at the top it may be hard to see, in the outlined red box is NT terminate process, which again, terminate process is a wrapper which eventually invokes this system call routine. And one of the first things it does is it looks at the thread that's responsible for invoking this routine, and it captures previous mode, and it passes that off to another function. And that function is called OBP reference object by handle with tag, mouthful. So what this function actually does is it looks, and it says, hey, is this a kernel handle? And the way a kernel handle is denoted is it's sign extended with FFFFF8. And after that check is done, it looks at previous mode, and it says, is previous mode 0? Well, if it's 1, that means it comes from user mode, right? And we should not trust it, and we don't want to look up the handle table in the kernel because it's originating from some process in user mode. But if it's 0, we infer, oh, this execution is coming from the kernel itself, and where's the kernel's handle table located at? The system process. So if we corrupt previous mode to 0, and then we invoke terminate process, this kind of tricks the kernel into looking up handles from the kernel handle table. So we can actually do this in our exploit. So in this example, it may be hard to read. We open up a handle to the thread that's performing all of this in our exploit, which is the current thread. So we open up a handle to our own thread. We leak the kthread object associated with that thread. Again, perfectly valid Windows exported functionality you can do, not a vulnerability. And we leak the kthread object, which is a kernel mode address. We then can corrupt the previous mode member of kthread to 0. So now what happens? Anytime this thread makes a system call, the kernel thinks, oh, this is originating from the kernel. So now what we basically can do is we can use ROP to call ZW open process and obtain a kernel handle. Then we can clean up our execution, which we talked about with terminate thread, and then we can use our vulnerability to corrupt previous mode and set it to 0, and then using that same thread call terminate process. Again, this would have been a lot easier to just have a shellcode blob in the kernel, mark it as executable and run it, but that's kind of the point of this talk is we can't do that anymore. We have to get very convoluted with these sort of things. So I won't press play yet, but on the right-hand side, this is process hacker. And that you can't see really, but it's msmp-eng, and that's showing our process is running, the defender process. Let's see if this plays. So now we run our exploit, and if we keep a look on the right-hand side, give it a second. No, I was not brave enough for a live demo. Oh, did I? Oh, it's not. It paused halfway through my video. Can't even get the pre-recorded demo right. And if we look on the right-hand side now, there it goes. The defender process is terminated. So that would have been a lot easier to do in shellcode, but again, we can't do that anymore. So last part, we've kind of said, oh, HVCI is really cool, right? But it doesn't really matter because we can get more convoluted and take care of it. That's actually not the case. We'll talk about how we augment HVCI. So what did our exploitation rely on? We flooded the stack with a bunch of fake return addresses, correct? Well, with the advent of Intel CET, which is a hardware mitigation, that's actually no longer possible. So what CET is, it's control flow enforcement technology, and it's a hardware mitigation that protects the integrity of the stack. So earlier we talked about when a call happens at the assembly level, what will happen? A return the stack. So in this case, we're calling the function foo, and its return address is pushed onto the stack. But now we have something called a shadow stack, which is hardware protected, that software technically can access for checking purposes, but not anything that could be corruptible, because if you're in user mode, the checks are done in the kernel, so you need access to the kernel. And same thing here. If the checks are done if you have CET running in the kernel, it's protected by HVCI. So that's kind of why I'm bringing this up here. So in this case, we have a stack. We push them onto the stack, the return addresses. So now we kind of do what we did with ROP, right? We corrupt the return address. But we actually have the shadow stack, which is an immutable copy of the stack. And then anytime a return happens into the stack, we check that with the shadow stack to ensure nothing was overwritten. So if you override a return address, you crash. So that's the end of ROP with CET. And what did our whole thing rely on? We flooded the return address with ROP, or excuse me, we flooded the stack with return addresses, and we can't do that with CET anymore. So the way this goes with mitigations is your mitigations are only as good as their resiliency. And I know that sounds kind of redundant, but HVCI does what it's intended to do. You cannot execute unsigned code anymore. But it's not resilient until you implement something like CET coupled with it that totally prevents even other things like code reuse. So the conclusion here is these mitigations are great, but they complement each other. So just depending on one, it'll help you with out-of-the-box exploits, but the more determined attacker, not so much. But what's interesting too is Windows only uses the shadow stack portion of CET. So CET actually is twofold. It checks return addresses with the shadow stack, but there's also something called indirect branch tracking, or IBT, and that is checking jumps and calls. Well, Windows already has CFG, and they have a better version of CFG called Extended Flow Guard, or XFG. So Windows actually only uses the shadow stack portion of CET. It doesn't use all of it. So to keep a technique like this alive, basically you would need to find a bypass in CFG or XFG, because control flow enforcement technology is a hardware mitigation, right? You can't access it in user mode, and the shadow stack, excuse me, or in the kernel. So believe it or not, these are all free mitigations. Well, technically not free, because you need supported hardware to do it. And that's my last little 30-second tangent I'll give. It actually wasn't the TPM that was responsive. These mitigations are enabled by default on Windows 11. TPMs have been around for a very long time, actually. There's another hardware mitigation called MBEC. It stands for Mode-Based Execution Control. And Windows has a software implementation of MBEC for CPUs that don't support it. Well, that software implementation is much slower than the hardware mitigation MBEC. But in order for HVCI to also be resilient, you need MBEC, which is outside the scope of this talk. And Microsoft didn't want their OS to be slow, obviously. You don't want to use the software implementation if you don't have to. You want to use the hardware. And that's where the CPU requirement really comes in, but I don't know why it went under the guise of TPM, because those have actually been around for a really long time. So these are all available for free. You can enable them on supported hardware, and yeah, that's the end of my talk. So if you have any questions, I'm happy to take them now or later. Yes. At the same time, kidding. Development debugging. Okay, so believe it or not, most of us are probably familiar with, like, if you've ever done basic buffer overflows, immunity debugger or some debugger like that. Windows has their own fully supported debugger called WinDebug. WinDBG, some people, that's not, you'll get a lot of flack for saying it that way, but that's how it's spelled. And it's a fully supported debugger by Microsoft, and it's can do kernel debugging. So all of these other debuggers can't really do kernel debugging, and it's all supported by Microsoft. So what's cool is you can parse memory as objects that are supported by Microsoft, for instance. So they publish what their public symbols, which contain all of the like notations for all the function names, object names, etc. And then I also like to use a disassembler, IDA. I'm sure you've probably heard of it before. And I kind of augment them together. So I'll use IDA for like static analysis, for instance. What is this kind of doing at a high level? But IDA can only get you so far because there's a dynamic component to it. What is the code actually doing while it's running? So I'll kind of couple those together. And another one is strings utility. So parsing a binary, where's the mem copy happening at? Things like that. So yeah, and there was another one. Yeah. Yeah, so that has to do with just the, like we saw, for instance, with a suspended thread, right? The APC is handed at the kernel level, so each thread for instances like that, where that's done by the kernel, interrupt, and it's got to be in context of a given thread. That's why there'll be an associated kernel mode stack with the user mode thread itself. So no matter what you're doing, there's always a portion of the stack, kernel mode memory reserved, the stack, for any given thread. It depends on where the execution is. So execution, depending on if it's in the kernel or in user mode. But it's not like a one-for-one copy, right? So the user mode data isn't located on the kernel mode stack, for instance. Yeah, good question. So Windows doesn't fully support it, but there is a mitigation as well. It's called supervisor mode access prevention. And what that does is it also prevents accessing data in certain instances in user mode. And it's just not good practice, really. The best practice really is like in a system call, for instance, you safely copy the parameters down into the kernel and then deal with it that way. A lot of drivers, they'll just arbitrarily copy stuff into the kernel and do things like that. You don't want to do it. That's why we have that previous mode, for instance, because it says, hey, I know I need to run these checks now in the kernel to handle this untrusted input, essentially. It's a tough design flaw regardless, right? Handling user mode data in the kernel or vice versa. Because you also don't want to leak kernel mode addresses. You know, if you access things in the user mode portion, if you do a bad copy or something, you may leak a kernel mode address up there as well. So that's that. Yeah. Yeah, yeah. So this demonstration was in a third-party driver, which we actually blogged about on CrowdStrike about like detecting all the typical market fodder type stuff. But these types of things, I think the Malaysian government actually was hit in 2021, I think with a Win32k bug, which obviously people are probably familiar with Win32k, not very great because of this wonderful gift Microsoft gives us of user mode callbacks, where the kernel will go directly into user mode and call things because it needs to be passed back down. So in native drivers, we do see this, but it's more targeted attack type thing, right? So if I can compromise a domain with domain admin, I'm not going to do something like this, right? But if I need something quick and that's well put together, like nation state level, in terms of I have a browser exploit that's paired with a sandbox escape that's paired with a kernel exploit, all packaged in JavaScript, user just views the browser, I've instantly got kernel mode access to their machine. That's really targeted operations because you have things like patch level, right? At every patch level, these offsets that you use will change where the code is actually located. So making the exploits, 40% of it, 60% of it, I'd say, is making it portable. So making sure it works in every single instance. So it definitely is, it's further and few between these sort of things, but they definitely do happen. And obviously, phishing is bad, but I don't think there's anything worse than like a remote code execution vulnerability, no user interaction, kernel mode access, for instance. So it's definitely something to pay attention to, but it's not as prevalent, I would say. Cool, well, thank you. Thank you.
80% of that was way over my head, but